So in this question, we are looking at a rocket. So immediately with a rocket, we should be thinking, oh, this is probably a question that's going to be about momentum. And in fact, the title of this question tells us that, but we don't see those in AP questions telling us what it's about. So when we see a rocket, it's usually about momentum. So we got a rocket in outer space, far from any other masses. Now, why are they telling us that, far from any other masses? They're telling us that to help us realize that there is no influence. There's no gravity or any other object involved, that we have this rocket by itself, and this rocket is the system. And so that rocket is propelling the satellite. The engines are turned on. Gases leave the rocket at a speed relative to the rocket. And you notice at this point, they haven't told us if the rocket is moving, if it has any velocity. And it turns out that doesn't really matter, but they haven't told us that yet. But they are telling us that the gases are going to leave. They're going to change their speed by that much. So that we could even label as a delta V. The gases are ejected at a constant rate of 1.4 kilograms per second. So in 1 second, we have 1.4 kilograms coming out. In another second, another 1.4 kilograms, and so on like this for every 1 second. The mass of the rocket is 280 kilograms. So 280 kilograms in 1 second, that 280 will go down to 278.6. In another second, it will go to 277.2. So what we see is the mass of the rocket gas system the mass of the rocket is decreasing, but it's not very much as a percentage. All right, so that's the information we have. Explains in terms of Newton's laws of motion why the rocket will accelerate. Why the rocket will accelerate. So Newton's laws. Well, let's first recap what those are. Newton's first law is an object wants to maintain its current velocity. That's the law of inertia. Newton's second law tells us that the net force is directly proportional to the acceleration. So if I double the force, the net force, I double the acceleration. And Newton's third law says for every force, there is an equal and opposite force. For every action, there is an equal and opposite reaction. So what we have happening inside this rocket is we have a bunch of gas particles. And once this opens up, the tail end opens up, the fuel is ignited, however, whatever's driving it to come out, the gas molecules are pushing on the front of the rocket. And at that point of contact, the rocket pushes back on the gas molecules, causing accelerations. The rocket is caused to accelerate forward. The gas particles are caused to accelerate backwards. So we have accelerations and we have forces. So what we would say is, according to Newton's third law, the gas exerts a force on the front of the rocket, and on impact, when it impacts, the gas exerts a force on the front of the rocket during impact, and the rocket exerts an equal and opposite force on the gas. These forces cause the rocket to accelerate forward and the gas to accelerate backward, respectively, according to Newton's second law. So that's why the rocket will accelerate. Now we want to use the law of conservation of momentum, how that applies to the motion of the rocket. So in this case, the system is the rocket and its fuel only. And that's why they were telling us there were no other masses to act on it. The system is the rocket and its fuel only. Therefore, the total P, total momentum of the system, must remain constant. The gas will have a change in momentum backward, and the rocket will have an equal and opposite delta P forward to ensure there is no net change in momentum. And so there's a couple elements here we need to highlight. So this is a 2-point question. And so certainly this is the first part. This is the easy part to get. That there's a momentum, change in momentum in one direction, there's an equal and opposite change in momentum in the other direction. The second part that's not so obvious and is fundamentally important is the assumption under which and through which the law of conservation of momentum can be applied, and is that there is no external forces to the system. The system is the rocket only, so there's no external forces, and so there's no possible impulses or changes to momentum resulting from something outside. It all comes from within. So next we need to estimate the speed of the rocket at 1 second. At 1 second. At 1 second, we've already figured this out. 1 kilogram of gas has been expelled. And we know the speed of that. So what we have is that the change in momentum of the gas must be equal and opposite to the change in momentum of the rocket. Change in momentum of the gas is m delta v, mg delta vg, and we have the change in momentum of the rocket, which is mr delta vr. And the mass of the gas is 1.4, and the change in velocity is 7.2 times 10 to the third. And we have minus the mass of the rocket, which is 280 delta V. So delta V of the rocket is going to be equal to 1.4 times 7.2 times 10 to the third, all over 280. I'm going to write that in scientific notation. 2.8 times 10 to the second. And when I write that in scientific notation, you'll see why I did so. 10 to the third and 10 to the second reduces to 10 to the 1. And 1.4 over 2.8 is 1/2. So now we are left with delta VR is going to equal to 7.2 over 2, which we can do in our head, which is 3.6, times 10 to the 1 meters per second. So the change in velocity of the rocket is 36 meters per second. Now, we don't know what the velocity was initially. We don't know the final, except we do know that whatever it is, the rocket changed its speed by 36 meters per second. And that's how we can apply the law of conservation of momentum to this case of the rocket.